Yeah, so we're effectively ahead right now. So in theory, since it's week 6, we're supposed to be still covering chapters 7 and 8, but we've already gone through those. And now we're going to be working on, obviously, the rotation part of chapter 4, which is nice because then that'll give us extra time, because in theory, that's supposed to be what we finish up next week. So like I said, we're doing great. So guys, don't ever hesitate to ask questions, to have me go ahead and elaborate on anything that you guys are having issues with, because like I said, we're doing great. I wouldn't mind spending more time on any of this information, especially obviously if you guys are struggling with it, because the goal is that you guys are going to be successful. Sorry, my wonderful sinuses are having a great time since we're going through the wonderful weather change, but at least there is markedly less ice and snow on the roads and otherwise. So we talked about angular motion, we talked about torque, and we talked about levers, okay? We've gone through all of this, and we're able to effectively talk about how we have advantages, disadvantages, and then how we can mathematically figure out something that is at balance, and then obviously how torque is going to go ahead and work around. Now, what we're getting into now is going to be the actual rotation portions. This is the same thing that we've covered previously. The only difference is now it spins. That's it. So instead of our linear velocity, so how fast something is going from A to B, we now have rotational velocity. So how fast something rotates around that axis. And then instead of having our inertia of really, we're just talking about our mass and then momentum of our mass time velocity. Now we're talking about effectively the mass of the object's resistance to rotating. Now, this doesn't include the friction that it would have from the bearings or whatever it's going to have for spinning about that axis, but this is going to be based upon not just the mass of the object, but its distance from the axis. So now any object is going to have an axis of rotation, so that point at which it's going to be centered along, that will then be rotating around. Now, the moment of inertia is going to be equal to the sum of all of those different center of masses and that radius it happens to have. So notice the sigma, that's the sum of all of them, of the mass multiplied by the radius squared. Mass, we're still working with kilograms. Radius, we're still working with meters. Okay? Now, in turn, everything is going to have what's known as a radius of gyration. And that's going to be the distance from the axis itself, where we're going to find that center of mass that it's going to be rotating about, okay? And that's going to be equal to essentially our mass times our radius squared. Now, this is really important to understand because it's going to be a natural component we're going to encounter when we have to do things like running. So, for example, when your arm is in a relatively short position, the radius of gyration is going to be up tight in the arm, but when your arm is in a long lengthened position, it's going to be further away. And in turn, it's going to be harder to go ahead and pull that arm through rapidly with your arm in an extended position, as opposed to bring your arm through when you have those elbows bent. So in this example of somebody sprinting, we've got the center of mass of the thigh, center of mass of the lower part of the shin or the shank, and the center of the mass of the foot. So we have a much smaller radius of gyration when we happen to have that bent knee position. Whereas when that leg is straight, notice those center masses are much further away. So we're going to have a much greater resistance to motion. Questions there on the radius of gyration or on inertia? Okay. The next big key is angular momentum. So before we had mass times velocity, now we are going to have that inertia multiplied by the rotational velocity. So this little kind of W looking letter, that's actually a lowercase omega. And that's what is going to be our unit for angular velocity. So how many degrees we're having to cover per second. Now, why do we care about angular momentum? Because when we happen to have a person who's spinning, we can control our radius somewhat. We can't control our mass, but thanks to the principle of the conservation of angular momentum, we're going to find that as long as we don't have any external torque working on an object, our initial momentum is going to always equal our final momentum. So if we have our initial mass, because we're not losing weight while we're in the air, we have the radius we're at, and we have that velocity. So if we want to increase our velocity, we have to decrease our radius. Or if we want to decrease our velocity, we have to increase our radius from the pre to the post. And this is the natural effect that people are taking advantage of when they happen to be doing something like a front flip or a back flip, because it's going to allow you to move through those positions. So let's have a little bit of fun. Fun being the operant term, okay? In order to not die doing a backflip, okay, you are going to have to be spinning in the air at about 360 degrees per second, okay? Your initial rotational velocity is going to be 60 degrees per second. And your initial radius, because we're going to assume that you're going to have your arms extended over your head, is going to be your height in inches multiplied by, we're going to go about 2.54 centimeters per inch, but we figure your arms are going to give you a little bit more. Actually, we'll go 3.0 now that I really think about where your head's at. Okay. What would your final radius need to be to get to that 360 degrees per second? Let's go and work our way through what we came up with. So this is our initial setup here, okay? Where we have, that's my mass, that's the height that I'd have with my arms stretched overhead. Notice that's squared, multiplied by the initial velocity of 60 degrees per second. So the final mass can be the same as 95, multiplied by the K2 squared, which we don't know what it is, or K, yeah. And then our rotational velocity, which we're looking for 360. So we factor this immediately. And then what we end up here is 210 squared, because 95s on both sides cancel out. 60 divided by 360 is 60. So this equals K squared. So then 210 squared is 4,400, or 44,100 divided by 60 equals K squared, gives us 7,350 equals K squared. And then we take the square root of that, and I came up with 85.73. And that was doing most of that in my head except for the square root. So obviously there could be a couple slight mistakes. But notice you're going from that 210, so that really stretched overhead position, to 85.73, which you're in a really, really tight little ball, which if you're thinking about that as far as converting it into freedom units, we're only talking about, gosh, what would be just a little bit over 30 inches tall. So it's a tight little ball that I probably would not be able to make into. Okay. So with angular momentum, what we then get is how do we change that angular momentum? This is what's known as angular impulse. And this is the product of our torque and over the time it happens to be acting. So effectively, our change in momentum equals our torque multiplied by the time it's being applied. So if we apply a greater amount of torque over a greater amount of time, we have a greater amount of angular momentum change. So, for example, if someone is going to go ahead and be on a diving board, jump off and go backwards, since they're rotating about that axis because the force is going up but the body's going backwards, we've got the amount of torque that's being applied to create that rotation and the time of which it happens to be where they're on the board, and that's going to give us that initial change in angular momentum. So everything we're doing here is going to convert over to the same equivalence of linear. So instead of mass, we're looking at our moment of inertia. Instead of force, we're looking at torque, which is literally just the force that's being produced multiplied by the distance from the axis. We have our angular momentum instead of our plane momentum, and our impulse instead of force over time. Now we're talking about effectively force times the distance from the axis multiplied by time. So torque multiplied by time. So when we go back to those Newtonian concepts, okay, when it comes to the law of inertia, an object is going to stay in motion unless it is acted upon by an external force. So it's going to keep rotating unless something acts upon it, or it's going to stay at rest unless something acts upon it. Angular acceleration is going to be always equivalent to the magnitude of the torque that's being produced, the direction that torque is being produced, and inversely proportional to the body's moment of inertia. Meaning, if an object has a huge amount of inertia, it's going to barely accelerate. If it has a huge amount, it's going to go ahead and go much higher. Oh yeah. Good job, Anouk. I messed that up then. Thank you for finding that. Let's double check. Yeah, great job. Check that up. Good call. So, angular acceleration is going to be equal to our inertia multiplied by that acceleration. So the torque we're applying equals our inertia multiplied by that acceleration. Or if remember what our inertia stands for, it's going to be our mass times the radius squared times our acceleration. So let's go ahead and work our way through let's go with a kind of a simple problem here, okay? So let's say you are looking at, those little carousels as a kid that you guys would kind of push, they'd rotate, you'd hop on and kind of spin around. Maybe. Okay, oh. So you're pushing a carousel that weighs 100 kilograms and has a radius of 2 meters. How much torque do you need to produce in order to accelerate it from its initial 0 to 30 degrees per second. So trying to solve for torque. Our mass is 100. Our radius is 2. And then our degrees per second that we're looking for is going to be 30. So then we have now, with our angular inertia and our angular acceleration, we then have angular reaction, okay? Which is for every action, there's an equal and an opposite reaction. So the amount of torque that one body is putting on the other is also being exerted on itself in the equal and opposite direction. No problem. Yeah, it's going to be a bit higher than that. Okay. We then have what's known as centripetal force, which is going to be force directed towards the center. And this is going to be due to an object that's rotating on the wall. So this would be, if you guys remember the old school, not old school really, but some of the like the carnival rides or like at amusement parks where you're in an object that's spinning quickly. Now, if you're being pulled up against the wall, you're feeling what's known as centrifugal force. That's pulling you into the back of it. Whereas that wall is pushing into you with what is known as centripetal force, because it's pushing you into the center to make sure that you don't effectively get pulled out. Okay. And this is going to be equal to the mass of the object, its rotational velocity, and the radius it happens to have. So centrifugal is once again where we're getting pulled out, and that's what you would actually feel. Yes, the gravitron, exactly. Now, what we're going to go ahead and do is, once again, I want you guys to go ahead and put up your wonderful group that you guys are in for our current, for your projects. Thank you, Kristen. Ugh. Excuse me, guys. Okay. So what we have here, guys, is a breakdown of effectively how you can figure out not just the center of mass, but the weight of each of the different parts of the body. So I'm going to go ahead and get you guys into your groups. So I slowly work my way through it. Thank you, Kristen. And Lexi, today I'm going to put you in with the free throw group so you don't feel like you're by yourself. Okay. Good. So now I just put some links up in the chat for you guys to go ahead and look at, where it's going to be an even easier way to see what I just put up here, specifically on the segments part, where you can literally figure out the weights of the parts of the body that you guys are doing. Now, our goal today is going to be, I don't want you guys to focus on your joint. I want you guys to focus on the joint that effectively none of you guys are doing, but just try to think about like, okay, here's, let's say, the foot. This is the percent of the person's body weight the foot should weigh. Here is where the center of mass should be in its length, and this is how long it should be, okay? From there, with that information, okay, now let's go ahead and figure out what would be that inertia. So it's rotational inertia, where we've got its mass multiplied by its radius squared. Okay. Now, once you guys have that, we'll go ahead and come back. So it's 10:07. We're going to come back at 10:15. We'll see what type of numbers you guys come up with, see if they look realistic, kind of work through them together as a group. Then we're going to have you guys go off and work on your own. And then you're going to actually look at that rotation. And so you know that actual rotational velocity. Now we can start figuring out those torques you guys need to use. Okay. So help each other out, work together, guys. And I'll see you guys back at about 10:15. Okay. We'll work through an example of one of these. Okay. So let's say I wanted to get the, like we'll go with something real simple. We're going to go with the weight of my foot. Okay. So notice this percentage. The weight of a foot in this example is 1.37%. So since I weigh about 95 kilograms, I'd multiply that by 1. Well, it's actually, remember, this is a percentage, so it'd actually be 0.0137. And that would be kgs, weight of foot, which I am definitely not feeling that saucy that I can do that in my head today. So bring over our handy dandy calculator. clear it out, take 95, multiply by 0.1 or 0.0137. My foot weighs 1.3 kilograms. Okay, so now we've got the weight of the foot. That's cool. Now we have the longitudinal length. Okay, now you guys did that anthropometric lab where you actually measured the length of all of these different parts. So you have your individual versions of this. Okay, now the question is, why do we care about that? Well, because then we can go at the longitudinal center of mass position. So now I know for a fact that my foot is literally a foot long. I wear size 13s, though I'm not tall, which the universe has a sense of humor, I guess. So that means my foot happens to be, instead of where you see the estimation here for the individual is 25.8, well, it's 2.54 centimeters in each inch. And so since I've got 12 inches there, that actually equates out to more along the lines of something like, we're going to say it's about 30 centimeters in length is my foot. However, notice the center of mass over here is 44.15% of that. Because if you think about your foot, most of the weight of your foot is back near the ankle. You know, it's much bigger there around your arch, and then it gets smaller as we get to your toes. So hence the center of mass is less than 50%. Okay, and most parts of the body are going to be like that, except for things like literally your upper arm, just because if we're going from top to bottom, it's more towards the top because where the deltoid's at, and then our head itself, because obviously most of the weight is at the top of the head, not at the bottom. So I'm going to take that and multiply it by 44.15. Okay. And this is going to give me a center of mass at, bring this bad boy on over again, because remember it's 44.15%. So that's why we put 0.44, because it's not like all of a sudden my center of mass is going to be like a couple meters past my body. It's obviously inside of that foot. So we have 13.245 centimeters. Because my foot is 12 inches long, so then 12 inches times 2.54 centimeters per inch, and then being lazy and not bothering with the 0.4 part. 95 is I weigh 95 kilograms. Okay, so now we've got the center of mass, we've got the weight. So in order to figure out our inertia, remember, we're going to take our mass times our radius squared. Okay, so that means I've got 1.3 times, and we're going to do this in meters, so hence it's going to be, I'll open parentheses to make it easy, 0.13245. It's in meters squared. Which means my rotational inertia for my foot, which is not impressive, is going to be equal to not much, 0.0228. Super tiny. Is that making sense to you guys? Awesome. So we're going to put you guys back in your groups. And now this time, I want you guys to pick one of your guys' joints that you guys are doing, and you're going to figure out that mass and that center of mass and kind of figure out that same inertia for just once. You guys can all help each other out. Let's say somebody's doing the shoulder. So then you have to figure out the center of mass then for what would be the upper arm, the forearm, and the hand. Does that make sense? So it's 10:25. We'll give you guys 10 minutes. See you guys back at 10:35 where you figured out that inertia. And then we'll go ahead and have you guys wrap up trying to figure out what would be the torque if you know the angle that that joint is going to have changed from, say, your preparation to your windup, or from your windup to your force producing. Make sense? I guess it does. Go for it. I'm going to record. If we're going to be looking at the hand and forearm, we got the center of the mass from this example of where it's at on the forearm. Okay. So we know that center of mass, we know that length, we know that weight, put those together. The next one, from the elbow to the hand. Well, the hand, notice it's got that center of mass, but that's going from the wrist to the hand. So we need to know the distance from the wrist to the elbow, add that to that distance from the wrist to the center of the mass of the hand, and then so on. Absolutely, Taylor, that's correct. Absolutely, Dakota. Yes, if you're doing the knee, you've got, now if you're doing something like a leg extension, then you just have the weight of the lower leg, so the shank, and the foot. But if we're lifting ourselves, you're going to go ahead and have the thigh and then effectively the hip, because the rest of the body is going to be directly above it from the hip. Anouk, you're unmuted. Thank you. Yeah, the hand is really, really small. And of course, in those examples, remember, again, the body positions matter. So if we're looking at the shoulder, okay, if I've got my arms straight, that's going to give that furthest distance for each of those center masses. But if I have my arm bent and tucked in, well, the center of the mass of the upper arm is still where it's going to be. But the center of the mass of the forearm, it's only the distance it happens to be from the shoulder joint to the center mass of the forearm. And that's where the math can get a little weird, but that's unfortunately what you need to go ahead and break down, or just do your best to try to go ahead and break down and look into. Does that make sense to you guys of what we've been doing so far with all this today? So then, if we go back to our happy little slide here. So from here, guys, we can now figure out effectively what is going to be our torque required to accelerate from the one point or the other, or to change our angular momentum. So take that initial velocity and now figure out what velocity we've gone to. And then you're that much closer to finding the solutions to all those questions on your projects. Questions, comments, concerns? So what you guys just found is going to be effectively, sorry, I'm going through my slides pretty quickly, is we just found effectively the moment of inertia. That's what we've been working through. Okay, and the axis of rotation that we're using in this example is going to be that joint. So for you guys, the forearm in your example you're doing is going to be from the elbow. Okay, so what are we really looking at? But then if we're going to really move the elbow, we need the hand as well. Okay, so hence why we're going to add that radius and where we're going to find that center of mass and then the mass itself. Now, once we have all of this inertia information, now we can go ahead, the radius of gyration hence depends on the position of the body, which makes it a bit more complicated. But from there, now we can figure out what's going to be our torques required to get those parts of the body to change. So notice the torque is going to equal, or torque multiplied by the time it took. And that's where we're going to watch the videos of your actual exercise. So you see how long each of those phases take. And from there, we're going to have our natural change in momentum because we're going to have our initial velocity and our final velocity. In certain cases, our velocity is going to be 0 because we were at a dead standstill. So then, for 1, and then we're going to have the velocity we've changed to. So obviously that's going to give us the torque we need to do. Or we're already moving, but now we're moving faster. And then the opposite is true. We can be slowing ourselves down. Like this would be the follow through after throwing a baseball where we're going to be controlling ourselves down. The videos are due with your projects, which are due at the very end of the semester. So you guys still got plenty of time on those, but that's why we chip away at this a little bit in those groups whenever we meet up so that you guys can obviously feel more comfortable with what you're doing, but you're going to be able to get everything done easily on time. And part of the method of which I'm approaching this with is we're getting you guys to work together in those groups. And I want you guys to really have to, play around with the information, really try to think your way through. And really, I want you guys to have to struggle with it, have to think through it and solve your own problems. That's going to be your project information. That's all up on Blackboard. It's both in your syllabus, and then it should be in just the general course documents. Okay, so if you're doing the knee, focus on obviously that thigh center of mass, but then you need to know how much of the weight is above the knee, and then that center of mass is going to all be based on effectively the hip, because that's where all that weight is coming down at and pushing through. That's the easiest way to do it. Now, you're right, Dakota, if you wanted to really make this kind of a monstrosity to you, you can then look at kind of the center of mass and do all of the different angle calculations for where the head, the torso, the arm, both upper arm, forearm, and hand are all going to be in location. Plus, if you guys are doing a movement like the clean and jerk group, you've got the extra load of the barbell that's obviously going to be in the hands, which is then being received through the shoulders, torso, hips, thighs, and then finally even through the lower leg and the feet. And so there's going to be different forces you're going to have to produce at each of those to overcome that extra load as well. So it's a lot, guys. That's why we're chipping away at it slowly but surely. That's all we've got for today. Stay safe out there, guys. We are done with chapter 4, but I think none of us really want us to go on yet from chapter 4 yet. So we're going to do some more examples of this on Thursday. So your guys' little take home is to come to class on Thursday with some things that you guys want to go ahead and work on, and or we're going to spend more time working in your groups. So sorry, I've already had you guys for an extra minute. Stay safe out there. Take care of yourselves, and I will see you guys Thursday morning. Bye-bye.